get to stay home and not have to go out in this crazy cold weather, but maybe you're all hoping you were back at PEP. I know I miss seeing your faces. Let me try to fix this mic here. So there we go. That's a little bit better. So this video is going to go over section 6.3, and let's go ahead and get started. Let me share my screen. All right, here we go. So I want to talk to you today about section 6.3, and it's kind of a new section. We're going to talk about something called similar polygons. So polygon, remember, is any figure that meets the criteria of having straight sides and all meets up. I mean, a triangle is a polygon, a quadrilateral is a polygon. So this applies not just to triangles. Obviously, we're going to talk about triangles because how can we not, right? But we're going to talk about something called use similar polygons. So the first thing that I wanted to talk to you about is what is it for two things to be similar to each other. So you guys get this special picture that my other classes don't get. Hold on, I'm going to adjust my mic again. Again, I'm sorry if this makes it really loud for you. Okay, that's a little better for me. I felt like I was kissing the microphone. All right, so we're talking about similar polygons. So that's kind of a new word for us, right? And so right here, there's a picture of the different terms that we've talked about so far. So we've talked about what it is to be congruent, right? Congruent means you have all your sides are congruent, right? And all of your angles, when I zoom in, it doesn't look very good. All your angles are congruent. So you can see right here, these three triangles, they're all appear to be congruent together. Geometrically, we would really want to see, something like this. That would be an angle, side angle, that would tell us that these triangles are actually congruent to each other, right? But you guys can see that they all look the same. So what we're talking about today isn't congruent because we spent an entire chapter on that. You're like, okay, great, I got that. What we're talking about today is what does it mean to be similar? So if you look at these three triangles, it's pretty obvious that those three triangles are not the same, just like our congruent ones over here, right? What it means to be similar is it means to have the same shape, but to be in a different proportion. Okay, so these three triangles have the same shape, but they're in a different proportion. In similar polygons, again, that doesn't just apply to triangles, in similar polygons, it means that all of our angles still are all congruent to each other. And that's true for a triangle, quadrilateral, whatever it might be. So in similar items, our angles are congruent, but our sides are not. They are what we call proportional. Proportional. And we just talked about, I'm going to spell proportional wrong if I don't look. I still might spell it wrong. All right, and we just spent the last section, 6.2, talking about what something means to be proportional. So voila, why do we talk about proportions? Because we need it for similar triangles. So what I mean in this picture, if these three triangles are similar, that would mean that all of these angles are congruent to each other, right? All the angles are congruent to each other. And I could keep marking that up. But it does not necessarily, it doesn't mean that the sides are similar. So this could have a side of 5, and then this one would have a side, let's say, of 10, and this is 20, right? If that's true, though, you have to have proportional sides on the bottom. So if this side is 5 and then this is 6, then this would have to be 12 and this would have to be 24 because that would be in a proportion, right? We go from 6 to 10, we're doubling it, and then, 5 to 10, we're doubling it, 6 to 12, we're doubling it. So it has to be in a proportional relationship. And then, of course, down here we have neither. All right, so that's none of them. So, I mean, I guess if you're a technical person, you could say that all congruent figures are also similar, but not all similar figures are congruent, if that makes sense. Okay, so that's kind of an intro to what that is. So let's jump into the notes and talk about that. All right, so this is our notes, and this is example number 1 from our notes. And so the first thing that you'll notice here is it says in the diagram, triangle ABC, and then it's got this little squiggly line is something to triangle DEF. Well, that little squiggly line means congruence. So I'm right here, and I'm pointing out this lovely little squiggly line right there. All right, sorry, I just said congruence. That squiggly line means similarity. Okay, so I should write that down since I just said the words wrong. This means similar, right? This means congruent. And it kind of makes sense, right? Congruent, everything's equal, but we got the little squiggly to kind of help us tell it's congruent. Similar, you don't get the equal part, you just get the squiggly part. So what this is telling me is that I have two triangles here, ABC and DEF, and they're similar to each other. Just like when we were talking about congruent statements, the order in which you write and name your triangle is important because that tells you that that the corresponding parts of the first triangle are similar to the corresponding parts of the second triangle. So that statement, again, is important. You can look at your picture and kind of see how they're similar to each other, right? They look like, you know, from A to B is 10, from D to E is 15, so it goes from 10 to 15, and then B to C and E to F goes from 8 to 12, and then A to C to D to F goes from 12 to 18. So they seem like they're similar, but let's kind of talk about that. So what it asks us to do is number one, or number A, to list all pairs of congruent angles. So I'm going to use this little space over here, making all kinds of space. Use this little space over here, and we want to list all pairs of congruent angles. So what you can do is you can look at the picture and kind of see, but the foolproof way is to go back to your similarity statement, just like in congruence, because it should be in order. So angle A has to be congruent to angle D because they're in the same position in your statement, okay? And then angle B has to be congruent to angle E, and angle C has to be congruent to angle F because it's in the last place. So the angles are actually all congruent to each other, and that's pretty cool, right? All right, so that's the first part. The second part is B, check that the ratios of the corresponding side lengths are equal. So remember, for something to be similar, the angles have to be congruent and the side lengths have to be proportional to each other. So what we're going to do is we're going to make a ratio because a ratio is a proportion. So we're going to make a ratio and we're going to check it out and see if it actually works here. Let me make a little more space here for myself. Okay, so I'll do this in blue. All right, so we're going to do part B here. Okay, and part B says check that all the ratios of the corresponding side lengths are equal. All right, so again, I'm going to use my similarity statement because I know the first segment in my similarity statement is A to B, right? And that's similar to D to E. You see that, how I'm using the first two letters of my similarity statement up here and here? And so then if I plug in the numbers, that A to B is 10 and D to E is 15. So my first side length is in a ratio of 10 to 15, which is a fraction that we can simplify, right? This is the same as 2/3. All right, but wait, I'm not done. It says check the ratios of the corresponding side lengths are equal. So I need to check all of them. So I'm going to check the next set, which is B to C. So is B to C over E to F? What is the ratio of those two things? So B to C is 8. And E to F is 12. Again, I can reduce my fraction, right? 4 goes into 8 2 times, 4 goes into 12 3 times, so 2/3. Okay, and there's one more, of course. We've got C to A and F to D. So we've got C to A and F to D. Okay, C to A is 12 and F to D is 18. All right, can I reduce that down again? Yep, they both divide by 6, right? 12 divided by 6 is 2, 18 divided by 6 is 3. And voila, what do you notice about all three when I compare the three sides? They all have the same ratio. So do you think that that's a coincidence? Nah, it's not a coincidence, right? It's because in order to be similar, which they've told us that they're similar, all the side lengths have to be proportional to each other. So that means that all these side lengths are proportional to each other, which is what we were hoping for. Okay, so they all equal 2/3. They all check out. They're good to go. All right, And then the last thing is asks us to write the ratios of the corresponding side lengths in a statement of proportionality. And then there's a little bubble over here off to the side. It says, in a statement of proportionality, any pair of ratios forms a true proportion. Okay, so that's great to know, right? So what is a statement of proportionality? That basically says that because AB over DE equals 2/3 and BC over EF equals 2/3 and CA over FD equals 2/3, then all of those equal each other. So part C here, my statement of proportionality, I'm going to leave part B up over here so you can see. To write a statement of proportionality, what you would say is AB over DE equals BC over EF equals CA over FD. Right, so I took each of these, and since they all equal 2/3, then they all equal each other. So that's how we're going to do similarity. It's pretty easy. 2 parts. Have to know the angles are equal. Have to know that the sides are proportional to each other. So let's do another set of practice with this. Actually, I'm going to do 2 more practice problems. We're going to do example 2 and 3 here, but let me clear off my screen a little bit because I know there's a lot going on here. Okay, so example number 2, you'll notice these are not triangles, and that's okay because we're actually talking about polygon similarity. So this applies not just to triangles, even though the rest of the chapter we're going to talk about triangles, but you'll notice these are polygons and they can also be similar to each other. So in this one, it says, determine whether the polygons are similar. So they don't tell us if they're similar or not. We got to figure it out. Are they similar or not? If they are, write a similarity statement and find the scale factor. So we haven't talked about the scale factor yet, but we will in just a second. Okay, so first of all, we got to figure out, are these 2 polygons similar? Right, that's the first thing we got to do. So remember 2 things if they're similar, right? Number 1 is the angles. That's what step 1 is here. Identify all the angles and see if they're congruent to each other. So let's check it out. These 2 diagrams, they're all marked up with angles. So it's looking pretty good, right? Angle B is congruent to angle K. Can you see that? They both have 1 line. Angle C is congruent to angle L. They both have 2 lines. Angle D is congruent to angle M. And angles A and J are both 90 degrees. They're both right angles. So angle A and J are also congruent to each other. So the corresponding angles are congruent. They're congruent to each other. So we got part 1 of similarity done, right? We've got angles that are congruent to each other. All the angles are congruent to each other. Awesome. All right. Now we have to start thinking about, before I would even go to the next step, is I would start thinking about how they match up. So if A matches up with J, right? A matches up with J. That's from right here, right? Those are congruent. B matches up with K. B and K are right here. C matches up with L. And D matches up with M. So what I'm doing here is I'm starting a similarity statement, and I'm going to see if this works out to be true, because this is my angles that match up based off of that. Okay, so now I'm actually going to check my side lengths and see if they're similar. So you see down here they've written it out, but just to show you, you would want to check, is AB, what is that ratio with JK? And they've actually written that here. What is the ratio of AB to JK? All right, so AB to JK is, AB is 8 and JK is 14, so 8 over 14. And can we reduce that? Yeah, they both divide by 2, so 4 out of 7. Okay, then you're going to check the next one in your proportional statement. So let's check BC over KL. So here's BC over KL. So B to C is 8 and K to L is 14. Does that reduce? Yep, 4 to 7. So check that off too. All right, then we're going to check CD over LM. So CD is 8 and LM is 14. Do you see a pattern here? And that's 4 over 7 when we reduce that down. And then the last one, right, we've got the funny one at the end, AD over MJ. AD actually is 12. Ooh, we get a different number. 12, and MJ is 21. So 12 over 21, those both divide by 3, right? 12 divided by 3 is 4. 21 divided by 3 is 7. So what do you notice about all the ratios? They're all 4/7, right? 4/7, 4/7, 4/7, 4/7. So all of the ratios are equal. So the corresponding side lengths are proportional. So that's good, right? So we've met the second part of similarity. We've got the angles are congruent and the side lengths are proportional. So here we can conclude, I just wrote on top of it, ABCD is similar to JKLM. Okay, and then something we haven't talked about yet, but it's pretty easy to figure out. It says the scale factor of ABCD to JKLM. What do you think that is? So the scale factor is how do we compare one to the other? Well, when we did our proportions, when we were comparing ABCD to JKLM, the factor that we got for every single one was 4/7. So the scale factor from ABCD to JKLM is 4/7. Okay, so there you learned something new. All right, one more problem like this, and then we will we'll kind of move on from that actually. So this one should be an easy one. And if you want to, go ahead and pause and you can try it and check your answer. So it says triangle B, oh, I think I cut off the letters on here. Sorry, that would help. This is B and D down here. This is B, and this is D. And this is R, and this is T. That would help. Okay, triangle BCD and triangle RST are similar. Find the value of X. All right, so since you know the triangles are similar, that you know then that the corresponding side lengths have to be proportional, right? So they've given you like the proportion side that you got to figure it out. So in that case, I know then that BC over RS, so BC over RS has to equal CD over ST. And then if I keep going, that has to equal DB over TR, right? I got that all out of my statement up here. I didn't even look at my picture. I said B to C, the first two letters, over R to S, the first two letters, has to equal C to D, the second two letters, over R, S to T, the second two letters, and then the third and the first for the last one, right? But really, when I think about the proportionality statement, what's important to me is I'm trying to figure out X, right, which involves this ratio right here. And I have two numbers for BC and RS. So here, I have those two. So this is the ratio I'm going to use to figure it out. So B to C is 12. R to S is 24. C to D is 13. And S to T is X. So all of a sudden, guess what I have? I've got a proportion that I can solve, right? So I can cross multiply, and actually I'm going to do something even before that, because I noticed that this 12 over 24, I can reduce that to 1/2 equals 13 over X. Do you see that? 12 to 24 is just 1/2. So when I do that, I get a much easier problem. I get X equals 2 times 13, or X equals 26, in order for this to be true. Okay. All right, so one fill-in, this is kind of hidden down under things, so this should actually be further up in your notes, and maybe I moved it in your notes, but it's not in my notes. But this box right here, what we're going to talk about is kind of what I already introduced in the last problem. So if two polygons are similar, then the ratio of any two corresponding lengths in the polygon is equal to the scale factor. I'm not going to make it in there, scale factor of the similar polygons. So again, if I was looking at this problem right here, and I wanted to know what is the scale factor from BCD to RST, look at when I compared BC over RS, I got 12 to 24, otherwise known as 1/2. So if I wanted to know what the scale factor of BCD to RTS is, the scale factor would be 1/2. Okay, so basically the scale factor is whatever ratio you find when you write the proportions. It's pretty easy stuff. Okay, let's do a quick practice with that, actually number 2 here on this checkpoint. So you can see there's two similar figures, okay, and it's figure FGHJ. FGHJ is similar to LMNP. These two are similar to each other. And then it asks, what is the scale factor of LMNP to FGHJ? So it's actually flip-flopping this similarity statement. Kind of make it a little tricky for you, but it's completely fine, right? They're still similar both ways. We just have to think about what goes on top. So we know that they're similar to each other. And so if we compare, we can pick any two numbers, but I'm going to pick the first two. To find the scale factor of LMNP to FGHJ, we would say, what is LM, because that's what's first, compared to FG, because that's what's first there. So then that's when I go to my picture and I see LM is 12 and FG is 15. All right, so my scale factor is 12 to 15, but we can reduce that, right? They both divide by 3, so 4 to 5. So the scale factor of LMNP to FGHJ is 4 to 5. Now, if I asked you to find the scale factor of this one, of FGHJ to LMNP, that scale factor would actually be 5 to 4. It would be flipped. Okay, and if you want a little extra practice and you want to know what the value of x is for this one, I'm not going to do it, but x would be 32. So if you want a little practice there, you can do that. All right, one more problem. Guess what? We couldn't get away without a theorem. This is our first theorem of the chapter 6. So let's go over this way and hopefully it'll look a little cleaner over here. All right, so the last thing that I want to talk to you about in similarity is it has to do with perimeters of similar polygons. So this is actually pretty cool. It says, theorem 6.1 says the perimeter of similar polygons, if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. Okay, so what that means is if you have two similar polygons here, in this example, it's KLMN and PQRS. If you add up the perimeter, just remember, means walking around the outside, adding up all the outside edges, right? If you compare the ratio of the perimeters, it's the same as the ratio of every single side. So this right here, this fraction that's shown right here represents the perimeter. That represents the perimeter, okay? And the perimeter is equal to the ratio of each side. So it's equal to KL over PQ. It's equal to LM over QR. It's equal to MN over RS. And it's equal to NK over SP. So again, I was just looking at my statement, doing the first two, then doing the middle two, then the last two, and then the front and the back. So basically the ratios that apply to your side lengths also applies to the perimeter. So remember back here in this picture where I said that the scale factor is 1 to 2, the ratio of BCD to RST is 1/2. If I told you that the perimeter of this was, let's see, 20. I'll tell you the perimeter of this is 20. Okay, would you have to sit there and figure out this other side to be able to figure out the perimeter? Not necessarily. You just know it's in a ratio of 1 to 2, so the perimeter of the larger one would be 40, because 20 over 40 equals 1/2. So it's kind of a nice little shortcut. All right, let's do one problem with this. I was planning on picking on Rivers for this one because I know she plays basketball, so I think she'll be okay with that. So Rivers is going to upgrade her basketball court in her backyard. Okay, so let me, no. Rivers is going to update her basketball court. All right, so the a larger I can talk. A larger cement court is being poured for a basketball hoop in place of a smaller one. So the small rectangle is the old basketball court, and the new rectangle is the newer one, right? So the new court will be 20 feet wide and 25 feet long. Okay, the old court was similar in shape, but only 16 feet wide. Okay, so my old court was only 16 feet wide. I'm going to put that on the inside. And my new court is going to be 20 feet wide. Okay, and then the new court is going to be 25 feet long. Now, notice the old court was similar in shape. So they throw that similar word in there. So that means that my court's just expanding. It's going to be the same shape, but it's just going to be bigger, right? The angles are going to be the same. So let's check this out. It says, find the scale factor of the new court to the old court. So I'm going to find the scale factor of the new court to the old court. And I want to find a scale factor, right? Well, let me look at my picture. I'm going to compare the widths because I have two numbers for that, right? The new court has a width of 20 feet and the old court has a width of 16 feet. Okay, so I can plug those in because I can compare them. They're my widths, right? And so if I do that, I notice they're both divisible by 4 and I get 5 to 4. So the scale factor of my new court to my old court is 5 to 4. Awesome, right? All right, so then the next part is, I'm just double checking my notes here. Okay, good. All right, the next part is find the perimeter of the new court and the old court. So one option is, well, let's find the perimeter of the new court first. Let's do that because that's pretty easy, right? So the perimeter of the new court, the new one, is going to be 2 times the length plus 2 times the width. All right, you guys memorize that. 2 times the length is 25, plus 2 times the width, which is 20. All right, and so the perimeter of the new court is 50 plus 40 is 90 feet. That's the new court is the perimeter. Okay, I'm just double checking, make sure I do anything. We're good. All right, so you could use this scale factor to figure out what the length is of the old court, right? That would be okay, and then find the perimeter. You can also use this theorem that you know that the perimeters are in the same ratio as the side lengths. Okay, so remember down here we said that the scale factor new to old is 5 to 4. And we now know, sorry, this is really messy, but we know that, let me give myself a little room. Well, yeah, I'm running out of room, but I think I got it. New to old, the scale factor is 5 to 4, right? We just figured out the new perimeter is 90 feet. So the perimeter of the old one should be in the same ratio. So we can solve this by cross multiplying, right? So we've got perimeter of the old court times 5 equals 4 times 90. Okay, and then divide both sides by 5, and we get the perimeter of the old court is 72 feet. So again, you could have used your scale factor to figure out what the length is, and actually I think I have it written down. I think it would be 20. Actually, if you use your scale factor for that. You could have done that, or you can just use this theorem 6.1 kind of as a shortcut. So, all right, so that's similarity. Remember similarity, 2 things. Angles have to be congruent. The side lengths have to be proportional, right? So that is similarity. I'll make a video for 6.4, but that one should be much faster than this one. So thanks for hanging in there, guys. I can't. Technology. All right. I hope you have a great day. I'll talk to you soon.